Hello everyone, I'm Yihao Chen from Tsinghua University. Here I'm going to introduce our recent research, learning with semantics towards the semantics-aware routing anomaly detection system. We know BGP, or the Border Gateway Protocol, is crucial for keeping the global internet connected. It serves over 75,000 autonomous systems to establish inter-domain routes, whose amount has come to an impressive 960,000 in today's internet. However, BGP was proposed back in the 1990s without any built-in mechanism to verify the authenticity or integrity of the route announcement. This leaves it vulnerable to various anomalies caused by either deliberate attacks or misconfigurations, while cryptographic extensions like RPKI have been proposed to enhance BGP security. Their deployment is limited due to incentive issues. As a result, BGP routing anomalies continue to pose a significant threat to today's internet. In recent years, several BGP anomaly incidents have caused widespread consequences, leading to significant financial losses for internet users. So what exactly are BGP anomalies? Typically, BGP anomalies include BGP hijacking and BGP route leak. As illustrated here, BGP hijacking occurs when an attacker falsely claims ownership of a prefix they don't actually control, thus tricking other ASs into believing that the attacker is the rightful origin of that prefix. This is also known as origin hijacking. Or an attacker can also announce a fake yet more preferable route towards the actual origin, which is known as path hijacking. On the other hand, BGP route leak occurs when routes are propagated to unintended ASs in violation of certain routing policies. For example, this can happen if a route is mistakenly forwarded from a provider to another, or from a provider to a peer, from a peer to a provider, or from the peer to another peer. These leaks can lead to undesirable transit costs for the leaker and longer detouring paths, ultimately harming BGP performance and also security. Given that BGP anomalies still cannot be fully prevented in today's internet, detecting them becomes critical. While there's plenty of research on BGP anomaly detection, most have significant limitations. Traditional methods often require extensive configuration, like setting up internet routing registries, and may also rely on active probing, which is both time-consuming and hard to scale. They may also depend heavily on manual intervention from network operators, and are usually limited to specific anomaly types. While machine learning has been applied to automate the analysis of routing data, these methods typically come with high training overhead and demand large-scale data labeling and feature crafting, and produce results that are hard to interpret within the BGP context. Given these limitations, here comes the question. Is there a practical way to develop an unsupervised, interpretable routing anomaly detection system that does not depend on labeled data or feature engineering? Well, before that question, we first need to ask, what's the common indication of a BGP anomaly, something that occurs in both BGP hijacking and BGP route leaks? Intuitively, it's the drastic change of routing paths that almost always come with routing anomalies, but not usually seen in a legitimate route change. But how can we measure how drastic a route change is? Should we use geolocation? Well, that can be unreliable, as many ASs can have multiple points of presence in diverse locations. Or should we use BGP statistics, which can also be misleading as they vary by vantage points and might miss smaller anomalies that don't usually have a significant statistical change. So actually, what we really need is a quantifiable representation that is capable of capturing an AS overall routing behaviors, such as its ability to provide transit services or how easily it is to access transit services. We call this the routing role of an AS. This concept reflects an AS overall routing behaviors determined by its unique set of routing policies. The key idea here is that an AS routing role should remain relatively stable within the global routing system. For example, a tier 1 AS always maintains peer-to-peer relationship with other tier 1 AS and transits global traffic and wouldn't suddenly change to a stub AS. So if a route change involves significant change of routing roles, it's a strong indication of a BGP anomaly. If we can accurately learn the routing role of each AS, detecting anomalies would be simply a matter of spotting significant changes of routing roles. That said, how can we learn the routing role of each AS? So now we introduce Beam, our BGP Semantics-Aware network embedding model. This model learns the routing role of AS based on their business relationships, as these relationships largely determine the AS routing policies. As shown here, our Beam model uses AS relationships to build a graph that reflects the internet topology. It then performs graph embedding to generate an embedding vector for each AS to represent its routing role. Two key properties are captured in this embedding: AS proximity and AS hierarchy. AS proximity measures how closely two ASs are connected to each other based on their direct relationships or shared neighbors. AS hierarchy, on the other hand, quantifies the difference in the hierarchical levels in the global internet. For example, the difference between a tier 1 AS and a stub AS means a large difference in hierarchy. With a dedicated optimization objective, our Beam model embeds ASs into a vector space, where each AS routing role is represented by its embedding vector. This approach allows us to quantitatively compare differences between ASs, thereby reducing routing anomaly detection to detecting significant changes in routing role during a route change. And our work can fully integrate BGP semantics into its representation. Here we look into the routing role. We visualize the routing role learned by our Beam model in the 3D space. Generally, we can see here, these rows form a pyramid shape. The tier 1 ASs on the top cluster together due to their similar global transit roles, while stub AS is lower and more dispersed. We also evaluate pairwise AS difference in routing roles. Here, the first figure here, figure E, we can see it shows the first order proximity. That is, ASs with peer-to-peer relationships have smaller role differences. And also the second figure here shows that the second order proximity, which is ASs with more common neighbors, have more similar roles. Also, the last figure here, figure G, highlights the hierarchy. ASs with more provider-to-customer links between them will differ more in their roles. So these results confirm that Beam can effectively capture intrinsic routing characteristics. Using Beam, we developed our routing anomaly detection system with 3 key components: the Beam engine, the routing monitor, and the anomaly detector. The Beam engine trains the model offline with monthly updated AS relationships to learn routing roles and calculate path difference. The routing monitor fetches the real-time route announcement from multiple vantage points and extracts the route change. The anomaly detector uses Beam's learned routing role to identify suspicious route change with high path difference, grouping them and identifying the responsible ASs, ultimately offering interpretable results. For evaluation, we collect 18 reports on well-known historical routing anomaly incidents from 2008 to 2021, including 15 BGP hijacking and 3 route leaks, covering over 11 billion route announcements. We also compared our system to several baselines, including 6 variants of our system using alternative distance metrics or general network embedding models. We also benchmark against 2 state-of-the-art machine learning systems, one using word embeddings and the other using a supervised LSTM detector. Qualitatively, our system requires less training, fewer model updates, and detects a wider range of anomalies. And we also have an experimental result to evaluate them. We also deployed our system in a large ISP to perform real-world detection. We first analyzed the path difference scores of the route change. This figure compares the path difference between anomalous and legitimate route change. We can see the anomalous route change, which is colored orange here. They show significantly greater path difference than the legitimate ones. This demonstrates that VM can effectively distinguish anomalies from legitimate route change using path difference scores based on AS routing rows. We then replay the route announcement from the 18 historical datasets to evaluate the detection performance of our system. As shown in the table, our system detected only 18 confirmed anomalies within tens of alarms, with no false alarms for 6 datasets and only 5 false alarms in the worst case. In contrast, the baselines missed anomalies and generated more false alarms. We also deployed our system in a large ISP to perform real-world detection. We analyzed the generated results from 1 month. During this period, the system processed many route announcements, detected over 5 million route changes, and ultimately raised 548 alarms. This table presented here shows the impact of these alarms and also displays the daily statistics of the alarms. On average, our system identified approximately 17 alarms per day, and the domain expert from the ISP systematically verified the correctness of each alarm and found that 497 out of them indicated actual routing anomalies. This means our system raised the average of only 1.65 false alarms per day. This result demonstrates the effectiveness of our system in detecting real-world routing anomalies. In summary, we introduced the concept as routing rows, designed Veeam, and also developed a system to extensively evaluate the performance using both historical events and real-world deployments. Thanks, everyone. I'm happy to answer any questions.